Hello all. So this is the third progress video for our final project for EE542. So in this progress video, we'll be looking into the main part, that is the data collection part and the model building part. So I am here to explain the data collection part. Vikram will explain the data collection from simulation, and Mayank will explain the model development. So in this part, for our problem statement, we have finalized it to localization of a target using ray tracing from a 3D model. That is, we are trying to simulate a real world model with our generated 3D models. So here, we would like to perform ray tracing on a model. For this example, I've created a very simple model of a room, which is of size 3 by 4 with height 2.24 meters. And we have an obstacle within the room, that is a shoe rack, which is made of metal. So what we do here is we create the room and then we allocate the material by which it is made of, and then we try to perform ray tracing use ray tracing in MATLAB. So for this we had to write some basic code. In that we had to create the floor and ceiling objects here, and we had to triangulate all of the objects. So this is just a very simple representation of the room. After doing all of that, we assign the basic physical properties of each and every element. That is the metallic nature, the roughness, the IOR value of the particular material. So for our assumption, we have assumed that the room is made of concrete and the particular shoe rack is made of metal. So we assign it there, and then we export this particular model file, and then we perform ray tracing on this. So Vikram will discuss more about that, and data collected from that procedure will be fed to a model, which will then be used for prediction of location, which will be discussed by Mayank later.
Hello guys, welcome. In the previous year video, you have seen how you have seen Sarvesh's demonstration of our ray tracing diagram, right, of 3D model, okay, for our room, for our hall. So it is a roughly a 3 cross 4 3.71 cross 4.18. I might be messing up the exact dimension, but well, let us put it roughly a 3 cross 4 grid, rectangular grid with a steel rack in its center, in the center end, um, being displayed. Okay, so it is a relatively a simple uh, 3D model. Okay, that models our hall, but yeah, this even the simple model has a lot of complexities when you view in the wireless uh, domain, correct? Because there might be three main phenomena: reflection, transmission, and diffraction. These play really intricately into that environment, right? So what I did is, Sarvesh took care of the 3D model building part, the ray tracing part. What I focused on was uh, using importing that, taking that 3D model from him, and then simulating for that 3D model, collecting RSSI data. All right, by inculcating the path loss equation for that uh, uh, model, for that room, for that simulated room, right? So that is what I ultimately did. So let me show you my thing. So this is a function that I wrote. Of course, I've spent quite a time for this, but this is a relatively simple model compared to the model that I'm going to show next. So first, I actually used NVIDIA's Shiona for this entire operation, but NVIDIA Shiona is a link level simulator built in Python, which obviously built by NVIDIA. You can just judge it by its name. It has a native YAML library attached to it. Okay, so that's the advantage of NVIDIA's Shiona, and it is written in Python. So these are the advantages of NVIDIA Shiona. So we try to leverage that, but we found some difficulties working with it because of the relatively less documentation that is associated with the NVIDIA Shiona. So we tried working with it for about 2 days, and we found some struggles. So we thought of maybe using leveraging MATLAB for this operation, because MATLAB is a very big player in wireless. You know, it has a lot of experience with domain specific attributes attached to it. So we tried to leverage that, and MATLAB also, obviously has ray tracing libraries too. So it can basically import 3D models and then uh, and then work with that. Work with the 3D models and then do the ray tracing. So MATLAB has that capability, which we need. Okay, because previously in the previous video you might have seen us using an indoor path loss model. Okay, but it's just an equation. This time it's not just a simple equation. We import a realistic 3D model itself. Okay, something like a room. Okay, something that we collect from a real room. Okay, a real measurement data. To to first collect real measurement data, you need a real measurement place, correct? So that is what we simulated this time, a ray traced 3D model. Okay, so that was our work this week. It's main work. So we spent some considerable amount of time first on NVIDIA Shiona, and then we moved on to MATLAB because it offered better prospects. So yeah, so our I reiterate once again, our ultimate aim was to first do basically uh, create a Wi-Fi measurement system that can ultimately, given a map and given a target's RSSI vector, it should be able to predict his location. Okay, for any location, for a location where you not even have a trained data set. Okay, that was my ultimate aim, and that is what Wi-Fi localization in this day is tending towards. So that's my ultimate plan. So it's a big task, so we are uh, taking progressive steps towards it, and this is one such step in this video that we are showing, which is we are accurately, we have ray traced a 3D model. Sarvesh has done using Blender, and here I'm basically importing that Blender model, and then I'm importing path loss to this model, and then calculating the RSSI values. Okay, so it's like essentially simulating measurement from a real room, right? So I will walk you through it. So I'll actually show this code to you. So this is what I did. I wrote this code. So this is an indoor ray tracing model, and so the transmit power is obviously this is the transmit power of the APs. Okay, and the frequency is 2.45 for Wi-Fi. So these are understandable. So what Survey gives me is a STL. The models extension is a STL extension. So it's a STL file. So I do STL read, and I get all the dimensions of the room from that 3D model, and then define the AP positions on it too, and create a receiver grid, and basically initialize the matrix. And basically, this figure is for us to see, to visualize that 3D room, right? So, so I plot this, and then finally I also calculate the RSSI values for that 3D model. So for the calculation part, for the RSSI calculation, that is where the path loss model comes in. So path loss is calculated with respect to how the dimension of the room is, with respect to the geometry of the room. This is the biggest difference we have this week. Path loss is calculated based on the geometry of the room. So for example, if in a particular coordinate, if there is some object, the path loss in that coordinate should be really low. The path loss should be, there should virtually be no signal present in that within that block, correct? So something really low. If I within a wall, a concrete wall, the signal strength should be really low, so something like that. So our path loss model this time should be should not be ignorant of that fact. It should consider that as a very important factor. So that's what we did this time. So let me navigate to that part. So this is the RSSA calculation for every x and y. This is a three-dimensional localization that we did this time. So we added one more dimension to our localization, 3D, not 2D. Previously we worked only on 2D localization. This time we added the third dimension too. So this increases complexity, but this is more indicative of the realistic scenarios, right? So this is it, and we store the output in a RSSI CSV file, right? So these are additional functions that assist the plots, visualization of the plots, and this is the core function where we calculate RSSI, right? So it takes in the transmitter position, the receiver position, and then the geometry of that particular STL object, the 3D model, right? So this time the RSSI calculation has really the knowledge of the geometry of that particular room. So this is the biggest difference this time, and hence more indicative of the realistic measurement. So uh, that's the biggest win this week's work has, right? So yeah, so this is the distance calculation, and so we I will walk you through the function, but here we first check if there's a direct line of sight between the access point and the receiver, right? And if blocked, meaning if there's not a direct line of sight, then there would be a reflection, right? So it's not direct line of sight. There would be reflection. So if there's a reflection, obviously the RF wave, the reflected wave will first interact with an object and hence would lose some strength, right? And then it would arrive at the receiver. So it would be face rotated, and also it would have a considerable decrease in strength. Okay, so there would not just be one reflection; there would be multiple reflections. If especially if there's a metal rack, which we have modeled, uh, there would be complete reflection. So many reflections. So it's not just a simple path loss equation that we are blindly formulating. So it's a path loss equation that is understanding of the geometry of that particular place in which it is operating. Okay, so that is what we did. So free space. So if it is line of sight, it's just free space, path loss, correct? Else, it has a block loss of 30 dB. This is a relatively simplistic model that I have worked on first, because um, the next simulation that I'm going to show you is much more complicated than this. Okay, it just not just assumes a path loss of 30 dB if it is reflected. Okay, something more complicated. But this is the first iteration that I worked on, so I just wanted to show you that. So, and this is the RSSI, and free space path loss is just normal calculation. Normal, it's just equation. We just plug in an equation. For the blocked function, check LOS. This is what we used, right? Uh, so we check the ray direction, check if line of sight is blocked by any wall. So that's the thing that we are doing, and so we do all these operations. Ray direction, we find the direction of that particular ray, and what is the length. The ray length is obviously the square root of some of the components in that vector, right? So it's the norm, right? And then basically so this particular calculation is completely reflective of the geometry of the particular uh, room, right? Or whatever objects are in the room, um, it has complete knowledge about that. So that's the advantage this particular RSSA calculation has. Okay, not just a simple path loss model. Okay, this function ray triangle interaction, this is for the ray tracing. So particularly, just by it helps in rendering the 3D model with the help of this algorithm. Uh, so I don't have that much domain specific knowledge about this, but Sarvesh helped me with this algorithm. So yeah, and finally we call this function. So I will demonstrate to you how this function works. So resolution of point one, let's see, because it was gonna take much shorter time. Yeah, you see. So this is the realistic model. I mean, 3D model that Sarvesh gave me, and these are the access points, position of the access points, and this is the steel rack. Okay, Z X Y, and this is the RSSI distribution of that particular scenario. Right, you can see there is something blue across this particular across the steel. This is just a XY plot, right? So yeah, but, across this X and this Y, we can obviously this is a steel rack, right? The steel rack does not absorb wireless signals, so within it, it should be there should be virtually zero, uh, not virtually zero, nearly zero. I mean, yeah, both are the same. Sorry about that. So the signal strength would be really low. So this indicates that, and then near the access points there should be a good amount of signal, so we can see that. But yeah, this is not a very simple, um, path loss model. So it definitely takes into account the geometry of that particular room, right? So that is the biggest win this model has. So yeah, so that's about this. So let me close this. I can also show you the data set. So let me download this, right? And I can open and show you this. So this is the data set that we obtained. So this is just for sample, all right? Again, if you want more density, you can get a even more very realistic map if you increase the positional density resolution. This point 0.5 is very very low. You can do, so you want to do, you should ideally do something like 0.01, and it will have a really fine smooth heat map. Okay, that is really indicative of the proper uh, uh, you know proper path loss map. Okay, this is just for just a fast, just for demonstration. I showed you this resolution. Okay, so let me now navigate to the next code. So here, what I did is I added some more additional complexities. So let me show you that. So I just one second. Let me navigate to that part of the code. Triangle. So it has the same array triangle, line of sight check, and stuff. Huh. Yes. So this time it is much more sophisticated. It calculates the RSSI and assumes a multi-path scenario too. So not just assigns a 30 dB path loss for reflected rays. It accurately calculates how many reflections it has, and then calculates the path loss. So one more additional layer of complexity this time, right? And other than that, it also calculates the material. It also inherits the. It also extracts the material properties from the 3D model itself, which Sarvesh gave me as an OBJ file and a MTL file. I think this file. Yeah, this one. So this contains the material information about the in the room, properties of the materials in the room. So the concrete means the wall is concrete, and there's a metal material, right? Shoe rack. So that's metal. So this is the next layer of sophistication we added to our model. So this is a slight. This is definitely is a much more advanced ray traced 3D model. So for that, I need to now add some more additional functionalities to the code, right? So not just a simple 30 dB loss if it is a reflected ray, right? Calculate the right RSSI for multipath signals. Multipath means reflected, correct? So yeah, so if it's near field, then the path loss Frizz's path loss not path loss model is Frizz's path loss equation is not obeyed. So there's a separate model for that. If it's far field, then Frizz's we can use Frizz's path loss model. Okay, so I use that. and then calculate the power. So the reflected power is now adequately calculated, correctly calculated. It needs the receiver point, the transmitter point, vertices, phases, material indices. So it is also now, it has knowledge about the material type of the object surrounding that particular uh, you know receiver, correct. So all these things come into play, and then finally the total power is calculated, correct. And the channel is assumed to be a relay channel, so it's not a Rician channel. So there's still not much line of sight domination here. So yeah, so we can consider all those things. And yeah, so this is one very big change that I did. Materials. So read the MTL file and create the material. Use the material properties. So the signal strength loss would be proportional to the material, what material it is being reflected on, right. So and these are the uh, um, standard values of concrete permittivity. That is what essentially changes. So all these facts, and then I visualize the plot finally. So these are the changes. So let me show you the plot again, this time by decreasing the resolution because we don't have that much time. Five, you know you see. So we can see high strength across the AP positions, but low strength near the steel rack. But yeah, still overall it's a reasonable plot. If you want to see a good plot, you need to increase the density of the points, resolution, but it takes a lot of time to do that. It will take about 5 to 6 to 7 minutes for that. So yeah, but this is representative of the yeah, so for proper real measurement, we obviously need to go through that time, right. So yeah, so I just wanted to show you, demonstrate how this works and what we have worked on this week. So my next in the next part, Mike will show you show you how we gave these data sets to Mike, and he worked on the ML part of our project. So he will demonstrate that part to you. Thank you.
Hello everyone, this is Mayank Shrivastava, and I was responsible for the model building part. So for model building part, I used TensorFlow, and I saved the data in the data CSV file, which has the following parameter and XYZ value for prediction. So I split the data into 80 is to 20 ratio, 80 for training, 20 for testing. So this was the model architecture I went with. So this was a hit and trial method, and I went with the following model architecture, which has the input layer, dense layer, batch normalization, dropout, and then I made this. So after that, I trained it for just 10 epochs, just for training purposes, and I got a test accuracy of 99% with a loss of 0.9 loss. So this was some predicted and actual value. As you can see, it is showing good results for now. So I plot the other thing, such as training versus validation loss. So as you can see, it is gradually decreasing, which is very good for us, and accuracy is momentarily increasing, which is again a good sign for us. This was the X and Y and Z prediction. So as you can see, the predicted value, actual and predicted. So it has a very low variance, and this is was the error distribution. So uh, again, this model is not currently not perfect, and I am fine tuning this model for gaining higher accuracy. So this was the model architecture. I added an add layer for connection of these two different neurons, and then dense layer batch normalization, uh, dropout, then dense, then it has a, since we're predicting three values, it has an output shape of three. So yeah, this was the model architecture, and this is my update for now for machine learning model building. Thank you.